Good morning in North America, good afternoon in Europe, good evening in Moscow, Dubai, Mumbai, and the rest of the world, Far East. My name is Branko Deljan, and this is webinar 4 with Boris Feigelson and Dusan Simic. We have Boris in Washington, D.C. and Dusan in New York. You can see them shortly. They will talk just in a few minutes. And we are still waiting for more people to sign up, but we have a nice webinar today, very interesting, even for me and Dusan, who are in this for over 25 years. This is a webinar that we can learn from and really pay attention on each slide because it's very unique. So we finally published the book. It's quite big, quite thick. Those who have our edition 2007, this is 100 more pages and 10 more articles. And Boris Feigelson is one of the contributing authors who wrote a very nice article on HPHT grown diamonds. So let me show you the book content for those who didn't receive it. We already dispatched over 200 books. There is one big shipment still waiting for Australia and England, and then we'll basically keep our promise. Sorry for delay, but I hope you won't be disappointed. We added a few more chapters and we updated the old chapters. The only one chapter that stays the same is this background, because we could not make it better. We talk about type of diamonds and history. Then in a chapter of technology behind growing diamonds and major producers, we're repeating old one, but adding another 20 new producers. One of the major articles is Diamond Grow Overview by Boris Feigelson. You will see some preview today. We had Malai Harani on the first webinar, October 15, talking about CVD diamond production. We did have Tom Chatham, who is also joining us today on as a producer of HPHT grown diamond and CVD, one of the 4 who's still in business of selling diamonds. And we had also Frank Ripka last webinar on memorial diamonds. Now we're going next 3 webinars. We're now at the midway of 7 webinars. We are talking about, Sherry will talk about inclusions in diamonds, CVD and HPHT. And Dusan will talk in December and myself about identification of HPHT grown and CVD grown diamonds with the standard instruments and advanced certification with the patent and other new things that we discover last 10 years. So still every month something new happening in this area of HPHT and CVD grown diamonds. And then we also talk about fraudulent replicas, something new. The people make diamonds to look like a GA or other lab natural diamonds, and patent that Dusan will talk more on December 4th. So you know who I am. Most of you are my friends or colleagues. I started to work in GA in 1995 in New York, worked with Dusan there, another lab for a couple of years. Dusan then moved to India, moved to Vancouver, where I started the Canadian Geological Laboratory in 2008 now. I travel around the world, same as Dusan, visiting different places and doing research on diamonds and gems. I'm teaching in 17 countries, and those who come to my conference and George Spiramilus, we do it every year in different Mediterranean country. Last 5 years, I'm very active with the Branko Gems Gemological Research Industry Inc., doing education, doing books like this, promoting instruments, discovering something new, and working with the researcher like Dusan in the different areas. We published together over 20 research papers, mostly on diamonds, and Dusan work in New York and Mumbai. And maybe Dusan can tell us something, what's happening with your new movie that you travel around the world to make a movie about how to grow diamonds. Tell us what's happening, because many Americans are our friends who are joining us today, and Canadians and other people who they want to know about this movie maybe coming up.
Thank you, Branko. Ladies and gentlemen, dear colleagues, old friends all around the world, good morning, good day, good afternoon, good evening, and for Far East and Australia, stay with us. We will have today so many interesting things prepared for you. About the movie, It is postponed. The movie is ready. This is a documentary, 90 minutes documentary for cinema, Showtime production by awarded director Jason Cohn, that we are shooting almost 10 years all around the world, mostly about synthetic diamonds. And beside me as the main character, they are also talking Steven Lucier, Martin Rappaport, Techmat Sprinter, and a few very, very interesting people. And when premiere will happen really depends on the COVID. You know. Okay, Branko.
Okay. So now I think Dusan should introduce our guest. I never personally met Boris, but we talk a lot on the phone and over the emails, of course. I was in the laboratory in Novosibirsk where Boris was working in 90s heading the team to grow diamonds in Siberia. But Dusan will tell more about Boris and why he is with us. And he was featured in many movies. Actually, I saw Boris first time in BBC movie in 90s. So I think Dusan can tell us more about Boris, a real legend for us who are into diamond business.
Yeah, thank you. So also I want to say that since we started our webinars today, we have the most visitors, almost 100, you know, and welcome all of you. And I'm sure that you will enjoy the speech of our guest, Boris Feigelson. Branko and me are grateful to Boris, who really raised our work to a high level with his contributing article that he will, among other things, present today. The list of the successes that Boris achieved in his scientific research career is really long. And that is why I give word to Boris right now. He will say a lot today. So enjoy, and Boris, welcome.
Yes. So what we'll do, I'll just quickly give Boris a chance to be host, and then we can look at his presentation and ask questions. Very important while Boris is changing the screen. On the bottom of your screen, you have a Q&A button. Please, maybe you had some questions even before Boris started to talk, but during his talk, it will be for sure some challenges, some a new area that you've never seen. Even myself, we practiced 2 days ago. I've seen some presses that I never seen in my life. And I said, Boris, where is this coming from? He said, oh, this is something, he got it while he was visiting some facilities. And so it's very inside story. It's really inside story because there are very few co-authors of the book who grew diamonds, and Boris did for many, many years. And he's doing something else now in Washington, but he'll tell you more about his past, present, and maybe some future plans. Boris, please take over, and approximately half an hour. During this time, you're very welcome to ask questions, and then he will answer for last 15-20 minutes, and I will close in approximately 1 hour from now.
Thank you, Branko and Dusan, for the very kind introduction. And let's start. Good morning, good afternoon, and good evening, everybody. I will tell you today HPHT insider story, but it will be not full story. It will be not complete, and not because I'm so secretive. I will not just have enough time to tell you full story, but I will try to highlight things which I think will help you to understand better how to grow diamonds using high pressure and high temperatures. Let's start. So diamond, natural or man-made diamond, some it calls also synthetic, can be single crystal diamond, monocrystalline diamond, or polycrystalline diamond. And today we're not going to talk about polycrystalline diamond. It's a very different topic. So single crystal diamond. This is amazing material, everybody knows. with fascinating properties. It's the hardest material on Earth. It's ultra-wide band gap semiconductor with the highest thermal conductivity among all materials, including metals, like copper. It's the best host for the newly developing quantum applications, etc., etc., etc. And everything is because of its structure. It's built from carbon atoms, which very strongly bonded to each other and making cubic crystal lattice. But at the same time, all properties of diamond can vary in a very wide range. And it happened only because of this reason, because all these properties are determined by presence of defects. Some of these defects are microscopic, and we don't want to see them. It's inclusions, cracks, etc. But main defects which define and determine properties of the diamond are defects in the crystal lattice, on atomic level. So there are two types of these defects: intrinsic defects, which vacancies, dislocations, taking faults, etc. And also the impurities of foreign atoms, of different atoms, nitrogen, boron, hydrogen, etc. And these two types of defects can combine with each other. Impurities can combine with vacancies, etc. And they develop new defects, defect complexes with each other. And all combination of these crystal lattice defects influence all properties of diamond, including mechanical, thermal, chemical, electronic, etc., etc., etc. And also they define applications where diamond can be used. Why I start my talk from this slide? Because all technologies which are people developing to make diamonds, to grow diamond crystals, we can compare these technologies of the level of maturity only on how they're able to deal, on the quality, how they're able to deal with the defects in diamonds on atomic level. If we compare high pressure, high temperature, different type of technologies with each other, or high pressure, high temperature technology with CVT technology, everything comes to the point how well this technology can control and eliminate or introduce different defects in atomic level in the diamond to be able to make diamond for specific application. Let's make a quick glance in the history of the man-made diamond. The first recorded paper on diamond research was in 1772 by Lavoisier, where he discovered that diamond is an inflammable material and can burn as a wood or a coal, not like all other gemstones. In 1797, Smith and Tennant discovered that nature of the diamond is very similar to the nature of charcoal. So it's almost the same materials. And in 1879, Hannay published the first paper where he described his attempts to make artificial diamond. And after this paper, many scientists around the world conducted a lot of experiments trying to make diamond, reporting that they made it, but it never was confirmed. In 1939, the Soviet physicist Ovsei Lipunsky published in journal Uspekhi Chimie, which means success in chemistry, groundbreaking work for the diamond synthesis titled About Synthetic Diamond. It was clear guidance for any researcher how to make diamonds. Unfortunately, in the history of the man-made diamond, this work is not well known for public, especially outside the former Soviet Union. I will focus on his work in the next slide. And there is three another milestones in the history of man-made diamonds. The first man-made diamonds produced by Swedish company ACI, General Electric success in making synthetic diamonds, and the first report by Eversole on diamond grown at low pressures. Let's look now into two main forms of carbon, graphite and diamond. We know that it's quite easy to make graphite by heating diamond. But why it's so difficult to make diamond by transforming graphite to diamond? Lipinski was the first person who accurately answered this question in 1939, exploring carbon thermodynamics and precisely calculating the phase diagram for carbon. Oops, sorry. Pressure temperature phase diagram shows pressures and temperatures where diamond is stable and where graphite is stable. And equilibrium line dividing these two areas in two parts. We can clearly see now in this diagram that diamond is stable phase of carbon only at high pressures, because you can see here that at low pressures graphite is stable. And diamond is unstable at any temperatures at atmospheric pressures and pressures below 20,000 atmosphere. It is vital knowledge for the diamond synthesis. All previous attempts to make diamond were conducted in the area where graphite is stable phase. Lipinski also estimated what are minimum temperature and pressure to transform graphite to diamond. Let's look at this free energy diagram at pressure where diamond is stable phase. We see that Gibbs free energy of graphite is higher than Gibbs free energy of diamond. So graphite is ready to transform to diamond, but there is some energy barrier which prevents this transformation. Atoms in the graphite crystal lattice need additional energy to be able to move and to be transformed to the diamond crystal lattice. To give this energy, to arm this energy, we can heat. And while we're heating, we need also to increase pressure to be in the area of diamond stability. According to the Lipinski calculation, the minimum temperature for the diamond transformation to diamond is about 2000 degrees, and it requires about 60,000 atmosphere. But remarkably, Lipinski proposed how to lower required temperature and pressure for diamond synthesis. He suggested to convert graphite to diamond through dissolving graphite in the molten iron in order to lower the energy barrier. He estimated that in this case, the lowest pressure for the diamond synthesis will be about 45,000 atmosphere, and temperature which requires in this case for diamond synthesis about 1230 degrees Celsius, which is very close to those parameters which are used today in industrial diamond production. And this is how the modern carbon phase diagram looks today. It's very similar to the Lipinski diagram, except pressure and temperature axes are swapped. Pressure here and temperature is here. Now, looking at this energy diagram at low pressures, we can explain why diamond doesn't convert to graphite when it is not a stable phase. Existing energy barrier prevents this transformation, and we need to heat diamond to quite high temperatures to be able to convert diamond to the graphite. I believe that Lipinski's work helped researchers who developed the first diamond synthesis, but unfortunately, because of many reasons, he didn't get credit for his work. The first man-made diamonds were produced in 1953 by a Swedish company, Asia. The lead researcher, von Platen, for the purpose of diamond synthesis, designed and developed special multi-angle split sphere apparatus where he could create and sustain necessary pressure and temperature for diamond synthesis. But unfortunately, the company decided to do not publish the results for commercial reasons. And then in 1954, the research team in General Electric demonstrated diamond synthesis, which is widely considered today as the first man-made diamond demonstration. Another type of high-pressure apparatus was developed specifically for this synthesis, which is called belt apparatus. And after the worldwide advertised achievement, General Electric successfully commercialized industrial diamond productions. And I'd like to emphasize this message for you, that the key to success of making first diamonds in the lab was the development of specialized equipment. In case of Sweden, it's multi-angle split sphere apparatus. In case of General Electric, it's belt apparatus, which allowed to work at continuous pressures and temperatures sufficient for the graphite to diamond transformation. Now, let's try to understand how high pressure, high temperature diamond synthesis works from the point of view of thermodynamics. Let's look at the carbon phase diagram and zoom in this area where diamond synthesis is conducted using molten metal solvent catalysts. It's usually alloys of metals from our group of iron. It is necessary to melt the solvent catalyst first to dissolve graphite. This is why we need to be in a phase diagram at temperatures to the right of this line. Let's conduct an imaginary experiment. We'll place graphite together with metal catalyst inside of the reactor. Then put this reactor in the high pressure apparatus and apply high pressure below this equilibrium line. And heat to melt the metal. What will happen? Graphite will dissolve in the molten metal like sugar dissolving in the hot water. Eventually, it will saturate solution, creating saturated carbon solution in the liquid metal. And nothing more can happen. When we release the temperature and pressure, we will find out the same graphite inside the reactor. Now another experiment. We'll place graphite with metal at pressures above the equilibrium line. We melt the metal, and graphite is dissolving the liquid, saturating the solution. And what is next? We will find out that diamonds start to precipitate and grow from the solution. How and why it happens? We already know that at these pressures, the free energy of diamond is lower than of graphite. System wants to move to the low energy state. It is shown in this equation. as a difference between free energy of diamond and graphite, which is below zero. The larger is this difference, the larger is the driving force to form diamond from the solution. The driving force is becoming larger and larger at pressures and temperatures. Values move away from the equilibrium line here. This driving force is usually described by the term of supersaturation, which is determined by the difference between actual solute concentration and concentration and saturated solute concentration in the solution, in this case, carbon concentration. At pressures when diamond is more stable than graphite, it has lower solubility in the liquid metal than graphite. As a result, graphite dissolves in the liquid, saturates solution until carbon concentration in the solvent becomes higher than diamond solubility. The solution becomes saturated with respect to diamond. This is called supersaturation, which creates the driving force for diamond to nucleate and grow in the solution. And how does diamond synthesis happen in practice? Let's remember that synthesis is driven by the difference of diamond and graphite free energies at high pressures and temperatures. The typical charge for diamond synthesis consists of alternated layers of graphite and solvent catalyst placed in a high pressure reactor. The first step of the process is application of high pressure to the reactor. Then the charge is heated to the point where metal can be melted. And when metal melts, let's zoom in this area, graphite dissolves in it, and very quickly multiple diamond crystals nucleate and grow inside the melt. How many crystals nucleate and how fast they grow depends on supersaturation or how far from the equilibrium line synthesis happens. Carbon continues to feed the growing diamond crystals through the thin film of the molten metal until graphite is consumed. This is why this process is sometimes called high pressure, high temperature film growth. Crystals of different habit can be grown depending on temperature and pressure and supersaturation, which is created during synthesis. It is a very efficient process to produce a lot of small diamond crystals, diamond powders and grit. And can it be used to grow big diamond crystals, and how? The first step is to eliminate spontaneous nucleation of diamond crystals and use small diamond seeds to control how many crystals are grown. The bigger diamond we want to grow, the less seeds we should use to preserve volume of the reactor for bigger crystals. However, the largest known diamond crystals grown by transforming graphite to diamond are about 3, maybe up to 5 millimeters in size. This process didn't become reliable and consistent for the large diamond crystal growth. Let's try to understand why. Growth of any crystal is a very accurate process. To grow crystal without macroscopic defects like inclusions, cracks, and others, the growth rate needs to be low and steady for a long time. Atoms as building blocks should come to the surface of the growing crystals in a very regular manner. They shouldn't crowd it near the surface, and also they shouldn't be depleted. The well-controlled and steady supersaturation is a crucial condition for the steady growth rate and for the good crystal quality. At pressures and temperatures corresponding to values on the equilibrium line, there is no driving force for the graphite to diamond transformation and diamond growth. graphite dissolving in liquid metal doesn't oversaturate solution with respect to diamond. As pressure increases, it increases supersaturation. We can decrease supersaturation back to zero by increasing temperature. And supersaturation increases if temperature is going down. We can see now that supersaturation, which created by the difference of graphite and diamond solubility, strongly depends simultaneously on temperature and pressure. Any deviation of pressure and temperature from the required values changes the supersaturation, resulting in a different growth rates. At super high pressures, it is technically very difficult to create the same pressure and temperature consistently every time from one growth run to another growth run. So every time, the supersaturation and growth rate are different. In addition to this, diamond is more dense material than graphite. As bigger diamond grows, consuming graphite, it changes the pressure inside high-pressure reactor, resulting in constant change of supersaturation and constant change of growth rates. So, how the problem of the reliable supersaturation control was solved? Next imaginary experiment will help us to understand this. Let's place diamond in the high-pressure reactor with metal catalyst, and another small diamond on the opposite side. Apply necessary pressure and melt the metal catalyst while heating both ends of the reactor to different temperatures, like it's shown here. Temperature 1 is higher than temperature 2. And what will happen? The large diamond is dissolving and small diamond is growing. It happened because carbon solubility depends on temperature. At higher temperatures, large diamond dissolves. Dissolved carbon is transported from the large diamond through the layer of liquid metal to the small diamond at low temperature, where carbon has low solubility. It creates supersaturation near the surface of the small diamond. Carbon precipitates on its surface and small diamond grows. The supersaturation as a driving force for growth is determined now only by the difference in the carbon solubility at different temperatures. It is certainly much easier to control this supersaturation by controlling only the temperature difference. It is a new method to grow diamonds, and it is called high-pressure temperature gradient growth. It was developed in the 70s of the last century in General Electric. The main idea of the method is to apply temperature gradient between carbon source and diamond seed, carbon source and diamond seed, and transporting carbon to the seed through the thick layer of liquid metal. And how it happens in practice. This is typical high-pressure reactor for the temperature gradient growth. Inside of high-pressure container, we see the heater, and then we see carbon source, which separated from the small diamond seed by thick layer of metal solvent catalyst. First, we need to apply high pressures to this reactor when we place it in a high pressure apparatus. Then we need to heat it, and we heat in the way that temperature near the carbon source will be higher than temperature near the seed. And when metal melts, graphite carbon source will quickly transform to the diamond agglomerate using the mechanisms of diamond synthesis, which we described before. And then these diamond agglomerates start to dissolve in the metal solvent catalyst and transport carbon atoms to the seed, and diamond crystals starting regularly growing on diamond seed. And this is high pressure temperature gradient growth from molten metal solution. This is interesting image of the seed after growth of initial stage of diamond growth on it. You can see here that at the beginning, the small diamond seed was first dissolved to some level, and then it grew back to the surface where new diamond start to grow on top of it. And here are the examples of diamond grown inside of the metal after the extraction. You see how beautiful they look. And here we can see the diamond from the bottom here and see the trace of the seed. Left it here. Of course, this method can be used to grow simultaneously many diamonds. And how many diamonds can be grown simultaneously depends on the available reaction volume. And even few layers of diamond seed can be placed in this setup and grow multiple diamonds. In our short tour to man-made diamond history, I emphasize 3 milestones which made possible modern diamond production. The first was understanding which pressure and temperature and chemistry are needed for the diamond synthesis. And 2 other milestones was demonstration of diamond synthesis as a result of the development of the new high-pressure devices. Sustained high pressures and temperatures are now produced in a few types of high-pressure apparatuses with solid pressure transmitting media. These apparatuses focus large forces up to thousands of tons of big press through 2 or more strong anvils to compress a sample. The simplest piston in cylinder design incorporates a strong metal or tungsten carbide cobalt alloy piston that is inserted in a sample confining cylinder. These devices are rarely used at pressures for diamond synthesis owing to the likelihood of failure. Bridgman, who received the Nobel Prize for his work in high-pressure physics, introduced in the 1930s a simple device which employs 2 opposite tapered anvils that squeeze the sample like a vise. It is capable of very high pressures, in excess of 50 gigapascal, when well designed with sufficient massive and lateral angle support. However, it can create pressure only in extremely flattened disk. And Bridgman anvils become the starting point for development of all existing high pressure apparatuses which are used in diamond synthesis and diamond growth industry. Let's start with belt apparatus, which was designed and invented in 1954 in a General Electric company and allowed to demonstrate one of the first diamond synthesis. It incorporates features of both piston cylinder and opposed Bridgman anvil. 2 highly tapered piston-like anvils here compress a sample that is confined in a torus much like a cylinder, open in both ends. When Soviet Union started in the end of 50s, beginning of 60s, research and development in the diamond synthesis to be able to produce diamond, a new high-pressure apparatus was developed. The first design was quite simplistic, but sufficient for diamond synthesis at the industrial scale. It is used to oppose anvils with recess. The shape of the sample inside of the apparatus gave its name. In Russian it sounds chechevitsa, which literally meaning lentless. To increase size of the sample and reliability of the high-pressure apparatus, a new toroid type of apparatus was developed later. The toroidal shape of the recess allowed to apply pressure to larger volume and gave better lateral support for anvils. In parallel with uniaxial devices, which employ force along only one axis, multi-anvil apparatus was developed. Here, in this example, which I show the 4 tapered anvils, which are spatially arranged in the tetrahedral configuration to apply pressure to the sample in the shape of the tetrahedron. All these 3 types of apparatuses are exploited today for diamond production. I'd like to emphasize these very important messages, that all high-pressure diamond making machines include 3 main crucially important components: device generating pressure, high-pressure apparatus, device that is inserted in the 2 high-pressure apparatus chamber where diamond synthesis will occur. High pressure we call high-pressure cell, high-pressure reactor, high-pressure capsule, high-pressure assembly, and I described in the previous slide the high-pressure reactor for temperature gradient growth. And device, which is usually a few thousand-ton press, to apply force to high-pressure apparatus to generate pressure inside the sample. The successful high-pressure system for diamond growth should include well-developed all these 3 components. And now let's take a quick tour how these all diamond-making machines look. The first example is belt apparatus. Of course, it's employ very powerful press. And here is the schematic for toroid apparatus with high-pressure cell inside. And this is industrial belt facility. You can see how massive this equipment to produce diamonds. And this is belt facility, the whole factory of belt. Here we can see industrial toroid facility where big diamonds are grown today. And let's look at a big family of multi-anvil apparatuses. There's a big variety of these apparatuses. For example, polyhedral presses, and here I show the tie rod guided cubic press. There are anvil guide systems where anvils placed inside of the blocks and which are placed inside of the press, and they can move inside of the blocks toward center by when force is applied to these blocks to create pressure inside of the high pressure cell. And here, the split sphere varieties, split sphere apparatus varieties. It can be a guide system where we have segments of sphere placed in similar blocks here, and when force is applied to these blocks, these segments slide inside by generating pressure inside of the high pressure cell here. Or it can be oil system where split sphere segments are placed inside of the elastic membrane, which is placed in oil reservoir. And then pressure generated inside by pressurizing oil, which transfer the force through the elastic membrane inside of this apparatus. And multi-anvil apparatuses can work with high pressure reactors with shape of tetrahedron, cube, octahedron. And here's schematic of one-stage apparatus which create pressures in octahedron or in a cube. And multi-anvil split and multi-anvil apparatuses can have double stage, second stage, when instead of the high pressure reactor, inside of the sphere, second stage of anvils is placed, and then which creates space for the high pressure container, and then the pressure is generated in this high pressure container by applying force to both stages of the machine. Of course, all these high pressure multi-anvil apparatuses require press. There is one multi-anvil split sphere apparatus which doesn't require press. It's pressless. And the next slide, I will show it. It's here. It's high pressure multi-anvil split sphere apparatus BARS, which in Russian sounds беспрессовый аппарат разрезная сфера, and it literally means no press split sphere apparatus. And it's the smallest high pressure apparatus which is capable to grow large single crystals. And I have this picture here to use myself as a scale bar to show the real sizes, small size of this apparatus. And here we can see the whole parts of this apparatus and whole structure of it. This is high pressure cell, schematics and how it looks in reality. And this high pressure cell is placed inside of the space between anvils of second stage, which inside of the space of the spherical segments. Now we continue to assemble this apparatus and placing top spherical segments and close it. And how really pressure is generated in this apparatus? First of all, it has two elastic membranes which are placed inside of the massive metal parts. And there is small space in between these metal parts and elastic membrane where high pressure pump can pump oil and create oil pressure there. This oil pressure creates force which moves spherical anvils toward center. And the motion of these spherical anvils transfers to the motion of the anvils inside second stage anvils. And they transfer their motion to the high pressure cell inside, generating pressure. What do we have here? That we multiply pressure by reducing the surface area where we apply oil pressure to the external area of the sphere, to the very much reduced surface area of high pressure cell. And this is approximate ratio of how we multiply this pressure. We create pressure, oil pressure outside of the sphere about 1500 atmosphere, and it gives us opportunity to create pressure inside, which is necessary to grow diamonds 50-55 kilobar. And this is industrial bulk bars facility today, how it looks today. And of course, industrial cubic hinge press. And Chinese cubic press these days becomes a major player in industry, diamond synthesis and diamond growth. And there are many reasons why it's happening. And one of the reasons, this press is very affordable. Another reason is quite powerful. It can create high pressures in a very big volume. And it's readily available, so it's become a very interesting tool to be used for the diamond growth nowadays. And I made these slides to show the beauty of the diamond crystals grown at high pressure, high temperature. They have very different shapes. They may have different colors. And they are beautiful immediately after extracting from the growth. You can see it here. And this slide is actually the introduction to another very big story about complexity of the atomic structure and atomic defect structure of the diamond crystals grown at high pressure and high temperatures. Its complexity comes from the multisectoral nature of these crystals, because they grow on a very small seed and develop all possible growth sectors for diamond. And different growth sectors of diamond incorporate different impurities differently. So you can see here and see here, for example, the octahedral sector incorporates a nitrogen and boron much more readily than cubic sector. And at the same time, the defect structure of the growing and the high pressure, high temperature crystals is going on through the evolution during growth, because while diamond is growing, all defects inside of growing diamonds also are annealing and transforming to the other defects, forming defect complex, etc., etc., etc. So it can be a very interesting story, but of course we don't have time today to tell this story in a more detailed manner. And I needed to talk to make this slide about CVD growth, because we talk a lot about thermodynamics of diamond growth. And thermodynamics actually allows to grow diamonds at low pressures. And the reason for that is that even if diamond is not stable relatively to the graphite at low pressures, the carbon in the hydrocarbons has higher, gives free energy than carbon in a diamond. And this allows to precipitate carbon by reaction of the decomposition of, for example, methane as a diamond. Even if the graphite, of course, preferred phase for deposition during the growth in CVD, but there is hydrogen, atomic hydrogen, which always cleaning the surface and removing undesirable graphite and allowing diamond to grow. And this slide is very short introduction on differences between diamonds growing under high pressure and temperature and diamonds grown CVD diamond at low pressures. The first very noticeable difference is that diamonds grown at high pressure, high temperature are grown on the small seeds and have shape of real nice crystals with well-developed all crystal sectors, crystal growth sectors. While CVD diamond is grown on one direction and it looks like layer of some material, which is diamond, and to become beautiful, it needs to be cut, polished, etc. And it's always mentioned that benefits for the CVD growth is possibility to grow on multiple seeds, as it's shown here. But high pressure, high temperature growth also allowed to grow many big diamond crystals at once on multiple seeds, even in a few layers. And I'd like also to highlight here that crystal quality of the high pressure, high temperature diamonds is much higher than diamonds which are grown by CVD. This is the highest crystalline quality which is possible to grow. And these X-ray topography images show that very few intrinsic defects in the diamond, few dislocations, and only few staking faults there. And it's very important quality for diamond for the high-tech tech applications. And it's very important question for high-tech applications. Is it possible to grow diamonds of 1 inch or larger? And why high pressure, high temperature? Why high pressure, high temperature? Because it allows to grow the highest crystalline quality of the material. And in the history of development of new materials for electronic industry, it was crucial development. The crystals which are growing under conditions at equilibrium, at near equilibrium conditions, to make these crystals as high quality, crystalline quality as possible. And thanks to the Chinese diamond press, which is now acquired around the world, and it's very easy to acquire, we see that new future is coming. This is facility in Russia where big diamonds are grown, and these type of facilities are developed in many other places. And now we can see that it is possible to grow diamond of this size, which is almost 1 inch, and it has weight 116 carat. It's fascinating achievement. And I would like to finish my story with this slide, with hope that in a very close future, we'll be able to grow diamonds which will allow us to make this size of wafers to continue development of new electronics and other interesting high-tech applications based on diamond. Thank you very much for your attention.
Thank you, Boris, for a very interesting, extensive talk. I think you cover a lot. Of course, you cannot cover everything in 40 minutes you had. We cover more in the book, 15 pages. And now it's time for you. And we have really very diversified community, people mostly from America and Canada as expected because of time, but also from Europe, UK, Russia, believe it or not, India, and here one person even from New Zealand. She woke up 6 o'clock in the morning on Sunday morning, Gina, to listen to Boris and us. This is really amazing, and this is why we are doing these things, in creating books like that and offering such webinars to share the knowledge. So I think, Boris, I have two questions, but while I'm reading, do you mind just to pass me back the host, because I think Dusan has one technical question and I have maybe one or two not so technical, and then I will give you back the host if somebody wants to get specific question or specific slide, or they remember that slide. So so basically, while you're transitioning to me, I'll just Antoinette Metlens, she is a book writer and reviewer of our book. She has already together question from her. Basically, she's talking about different shapes and colors. I mean, you mentioned this slide, and question was if fancy color static diamonds are more difficult to find in some shapes because of this different growth, what I know, I can tell you from my knowledge, but I guess if you want to answer first, and then I can add to it. And then for same person, so one is about shape of color diamonds, shape of crystal, I guess, and what comes out. And second question is how many carats of colorless, near colorless diamonds you think are in marketplace over 1 carat? Difficult question. You wouldn't know this, but maybe you can estimate. Or do you think is the goal to grow bigger diamonds, or more focus on those sweet spot of half carat to carat and half? We talked about this with Tom Chatham in previous webinar. So if you can answer, Boris, and then you can give me the host.
I already gave you the host.
Okay, great.
Okay, so what is the first question? Could you repeat, please?
About shapes of the fancy diamonds. I mean, most of them are cubo-octahedral shapes. When the HPHT, is that determine the shape of the polished crystal, how they will look?
What determines the habit of the diamonds, which are grown at high pressure, high temperature, right?
Yes, how they look. Most of them, you can maybe repeat these shapes of these diamonds. She's talking about color diamonds. I guess the same as colorless, but
yeah. So the shape in general, first of all, depends on which phase of the diamond seed you grow. You can grow on a cubic phase of diamond seed, and then you will have the shapes. Probably I need to go back to my to my presentation to explain better, right?
If you want, I can give you back the host. Yeah, no problem.
Yeah, I think it will be probably better.
Okay, no problem. It takes 1 second. So you can show this slide about shapes.
Yes, 1 second.
There's another question from Randy, but I think I answered that question, unless Randy want to answer a different way about seeds.
If you look, do you see me, right, this slide?
Yes, we see.
Okay, if you look here, for example, these crystals were grown on the seed which was oriented by a cubic phase. So this is 100 direction, cubic direction they grow. And these two crystals were growing on the seed which was oriented on a octahedral phase of the seed. So if you look from top to bottom, you can see here the trace of the seed through the crystal, here and here. And it's octahedron phase. Mm-hmm. So this is direction 111, if you look from top to bottom. So this makes shape a little bit different. But habit of these two crystals, this and this, in both cases, octahedron.
Yeah.
It's a little bit different shape because of the orientation of the seed, but habit is octahedral. But sometimes you can have additional growth sectors which forms different faces on the diamond. You can see here, for example, this is on near the top, 311 faces. Here we can see probably cubic faces, and here we clearly see cubic.
Yeah, this is interesting. Faces. There's in the middle that cubic near colorless shape.
Yes, yeah, it's colors, crystals, yes. So the habit of the crystals, grown crystal, depends on many parameters. First of all, if we keep the same environment where we grow, for example, we grow diamonds with nitrogen, right? But we change temperature of the growth. This will change the habit of the crystal. Mm-hmm. So usually the pure octahedral, like this shape of the crystal, is obtained at a little bit at higher temperatures than crystals which have more crystal growth sectors and faces. Mm-hmm. If you go to the lower temperatures, you will see more and more cubic faces on the crystal.
Yeah. So thank you, Boris. And then, Antoine, just to finish, probably they will cut one round or one fancy shape out of mostly round from cubo-octahedral, and maybe different shapes if it's a different orientation. So this is the answer.
Also, the impurity very seriously affect the crystal habit.
Yes.
So when you grow colorless diamond, you avoid the nitrogen impurities, not just in diamond, you avoid nitrogen in environment where diamond grows. So you change the relative surface energy of the growing different diamond growth phases. And this is what defines the habit of the crystal, which is growing. But also temperature will influence of this habit.
Okay.
So it's complex relation between impurities and temperature, and pressures also plays its own.
Yeah, thank you. We have two questions from Tom Chatham, and I will read one of them. I can partially answer, but you also know, is AOTC still in business? I can say they were in first book 2007. They were very much in business, and they sponsored this book. They're now making presses to grow diamonds. This is their major business, what I know, AOTC. But you want to answer, you know, more or something more than this, Boris, you can answer. But this is what I know from Alexis Arakani.
What could you repeat the question?
AOTC is still in business. What I know, they're not selling gemstones anymore.
No,
diamonds. They're making presses.
I think the facility in Moscow doesn't work anymore.
Yes, this is.
They don't grow diamonds.
Yeah,
this is what I know now.
They're doing research. I was in the facility in Holland doing research and doing post treatments, but not growing for the market. And then why NDT is so good in growing white diamonds? One answer, I guess, is the press. They modify Chinese press, but you know better why white diamonds growing larger white diamonds. NDT from Russia, new diamond technology.
First of all, white or colorless diamonds are more interesting object to grow, right? And not just for gem market and for the high-tech applications, because it's nitrogen-less diamonds which have very low concentration of nitrogen. This is what research and industry needs. This is one of the main reasons. And the press itself, Chinese press, it just gives opportunity to have big volume where you can grow diamond, because it just provides you means or tool to create pressure in a big volume. It doesn't provide you technology itself to grow diamonds. So why NDT grow very nice diamonds? Because they have right people who know how to do this. This is probably right question.
That is a very good answer. Not only the technology and press to buy, you need to really good people who has experience, and they're working with the good people from Russia and Ukraine. So another question is, I can read the questions. Not all of them you're expert, but I will read them because I think it's respectful to read questions from people. This is about environment and eco-friendly process. One question from Gina Beretto from New Zealand. What you can tell us about efforts of diamond makers to create environmentally friendly process? In the same direction from Michael Schlamander from Austria, do you know the energy consumption to grow 1 carat of rough diamonds? If yes, is it more or less the same for small or big diamonds? Is there difference about 1 carat approximately? Energy consumption, I guess HPHT in this case.
Yes. Yeah, I know that.
You know.
Yes. I can give you example because it depends on what kind of equipment is used. It depends what kind of setup is used, etc., etc. But generally, what I can say, like in a bars, for example, right? The bars requires to grow 1 carat diamond. Okay, it depends what kind of diamond. If yellow, it requires like 3-4 days to grow this type of diamond of good quality. Or if you want to grow colorless diamond, it will require 6-7 days. It might depends. And the energy power which it requires to heat to these temperatures where we need to be, it's about 1.5 kilowatt. So you multiply this power by hours, and this is how much energy you consume to grow diamond. of course, you need to have a little bit more energy for heat dissipation. You need to cool also during process. So it's about maybe 2 kilowatts then as a total for the whole process.
Okay, so thank you. So thank you, Boris. If you can just transfer back for me to be host, I will show one slide or two. Dusan has a question, and while you're doing this, there is a question about fluorescence of white diamond. I don't know, Boris, if you are studied this or not. It's a question. Is it true at this time there is none of synthetic diamonds, white diamonds exhibit blue fluorescence? They mean blue fluorescence under long UV light, what is 365 UV source. And then you can give me the host and I will show more technical question from Dusan. Do you have an idea about that or no? About blue fluorescence of white diamonds?
I think you
know
better prepared now to answer this question.
I agree. So Antoinette, we'll talk more about this in December webinars, fluorescence and relation to the origin of diamonds. They're super rare, what I know so far, or I didn't see it. Maybe we'll talk about this more in December. So what we'll do now, it's just show a slide from the. I want to share. So I need to be host back, and then I can.
Okay.
Yeah.
You want to be
and
back?
we still have a few minutes for more questions, so no problem. We said 1 hour plus questions, so this is what we plan, and we're still okay. So you need to go to my let me see if no more questions so far. And I will use opportunity to share a question that Dusan prepared. Just a second. So Dusan, you can talk about this now. Your question about fluorescence and the type of diamond.
Yeah, this is a stone that Boris borrowed me for research 5-6 years ago, you know, and obviously we have a HPHT grown diamonds that is additionally HPHT treated, and we see what is a usual that fluorescence. What Antoinette asked that it goes toward blue fluorescence under 365, and what is even more interesting that long fluorescence is at least same or stronger than shortwave fluorescence. What today for gemologists is very unusual. And then the most interesting thing, what is happening, Branko, go to the next one. This is in FTIR that we have a pure 1AA diamonds. What is not what we don't see, you know. Usually there are two ways how it could be made, and this is a question for Boris, how it could be done, you know, because as we see here, that single nitrogen, what we are expecting to see only, is very, very low and high resolution in FTIR measurement. Okay, Boris, tell us how to.
Yeah, if you look in the luminescence, first, if you look in the luminescence, can you go back to the luminescence slide? So I think it's quite typical for the nickel nitrogen complexes to have this luminescence, and because the diamond was grown in an iron nickel cobalt carbon system, and it incorporates quite a lot, reasonably a lot of nickel atoms, and then at high temperatures, these nickel impurities are combined with nitrogen and form very different variety of very different nickel and nitrogen complexes. And the formation of these complexes depends on the temperature where diamond was exposed. And exposition diamond to the temperatures happens in two ways. During growth, because it takes quite a lot of time. So if diamond is grown at quite high temperatures, it's not only incorporating impurities from the environment, but also these impurities start moving inside of the growing diamonds during growing process. So we observe annealing while we grow. So the impurities are moving and they meet each other and they form the complexes. So it's very typical for synthetic diamond grown in iron nickel system. And if we look in infrared spectra, it means that diamond was exposed to quite high temperatures, and probably it was just annealed at temperatures high enough to be able to transform all substitutional nitrogen, which is C centers, to the A centers. And if diamond lattice has nickel impurities, they promote the kinetic of this transformation. In presence of nickel, the transformation of C centers to A centers requires less temperature.
This is very interesting, yeah.
Requires low energy barrier for this transformation. So it cannot be mixed with natural diamonds because it has very typical features.
Yes.
And probably it was annealed. But
yes.
I will finish that you can create diamond with 1A features, synthetic diamond, by growth. You just need to grow at reasonably high temperatures. And we demonstrated this in our paper in 1991 paper, where we have samples, diamond samples growing at temperature about 1700 C. And these samples, these crystals had only A centers. So.
Yes. So I think what Dusan very rightly wants to say, and we are emphasizing in this book, is not enough to use only one technique to identify lab-grown diamonds. If you just use infrared, don't check at fluorescence inclusions, you would say, oh, this is a natural diamond. If you just, of course, with fluorescence inclusions and other things, you have to combine 2 or 3 instruments. And we talk about these types of diamonds in page 36. This is and more about, we even show this infrared different one in 2007 that A are much bigger than B, 2007. So I can only say you need to read more in the book because each topic is covered. This is one little bit differences between Dusan and me, how we want to approach the book. We promised book of 130 pages. At the end up with 188 because Dusan was really pushing to publish as much information as possible, technical. We have 15 pages of CVD diamonds by Malai Hirani. And those who didn't listen to the first webinar, I really encourage you to go to we have YouTube channel. By the way, this webinar was YouTube live projected. I didn't want to emphasize too much because we didn't promote it. But beside 30, 40 people we had today on the Zoom, we had another double that on YouTube channel, and you just basically to search on the Bracon, Gems, and AG&J, what is Dusan's and my company. Also, Tom Chatham webinar is on YouTube. In 1 week that we posted there, we had close to 200 views. What is really interesting, people are watching these webinars, and it's much faster way to watch them. And we will post this one as well in probably 3 to 5 days. You can share with your friends. This is a link, but just search Branko, Gems, and AG&J, and you can listen to this webinar. This webinar is not posted because Frank Ripka did not want to make even bigger controversy in Morla diamonds. Who listen. Who didn't, will repeat it probably in January, February at the time for North America. And this is the next one. I will do exactly next Friday, same time, but on Friday, November 20th, with Sherry Woodring, our colleague, on inclusions in diamonds. One way to separate if you see such inclusions. And what I can tell you, it's about time to finish. So I really want to thank first Boris Feigelson because he is the main actor today, not actor, speaker and guest and researcher. We are just supporting his talk. And other people, Sherry, Malay, and Frank, who really write a nice article and make our book really strong and longer. And Antoinette Matlins, Richard Drucker, and Stuart Robertson from USA reviewed the book from industry point, and Alberto Scarani from Major Labs technically. Nilesh Shesh, Tom Chatham give us samples in the past, and for the next book coming up next year, Godwin and Mumtaz Gonzalez did the editing and design, and our colleague and countryman Nesha Popovic helped with these webinars and newsletters. We couldn't do it without our sponsor NCJV from Australia. I want to thank Kim Hughes and Gail Brett Levine from USA. She got her books finally this weekend for her NJ members. If some of them are there, expect next week to be shipped to you. And also, I want to thank Shirley Mitchell from UK for joining us and for sharing information in UK. You can order via JVA website. It's also posted on our website. A link to order in UK is much faster to order from Shirley than ordering from us, and it's better. Same in Australia, New Zealand. Please order from Kim Hughes. And this is basically what I need to say about this webinar. And the great reviews from people. It will be a review in a Gem Guide magazine soon, in Journal of Gemology. Even René Newman give us nice review on Facebook, and I'll probably show it next time. But those who wants to still order from us, we give $5 off for those who really come to these webinars. You just have to put book 5 off on the checkout and order the book from us. Anything else, if you want to say, Dusan or Boris, you're very welcome. But I think, let me see if there are any more questions last moment, and then we can close it. There's more questions, of course.
Thank you very much, Branka.
Let me see. I mean, for those who want to log off, it's fine, but we'll just want to see if there's more questions. Yes. Raymond Mason from Washington State asking about seeds. I know in literature it says they were using HPHT seeds, little crystal, and natural mine seeds. How often is really necessary to use natural seeds? Is it mostly HPHT grown as a seed to grow diamond? Boris?
No, we always use synthetic diamonds as a seed. It's much simpler, and they're very good quality. No point to use natural diamond seeds.
Mm-hmm. Okay. So that's about that. And just to confirm, Antoinette, to make sure that most diamonds are still type 2A. Yes, what I know, they're type 2A, but of course they can make type 1 diamond. Be careful, Antoinette, because yellow diamonds, they're type 1. There's type 1B with single nitrogen, and we'll talk more about types and this in the future. So this is, I think we answered all questions. Unless Dusan want to say something else, we are about to expire our time. Okay, maybe there is some chat here. I will check chat, and then we'll close it.
Oh, just to take to all guests, and stay with us, come to the next webinar, and we are trying to be interesting. Boris, thank you. Good luck.
Yes.
Stay safe.
Yes. Thank you all, and thank you for nice comments on the chat about the book and the webinars. And basically, without you, we wouldn't make such books. And thank you for reading it. Thank you for ordering. And hope to see you. The next 3 webinars are gemologically speaking. We send it in attachment to save time. Details, Sherry Woodring, then Dusan, and then myself in December before Christmas. So thank you a lot for joining us. And if you want to repeat, read something that you missed, we can post it next week on YouTube, and we will send you newsletter next week. Thank you, Dusan. Thank you,
everybody.
Boris. Спасибо, Boris. Hvala, Dušane. Until next time.